phi is a matrix, right?
No, phi is the angle of rotation.
Okay.
Scalar.
Yeah.
And this is a matrix. Okay. So we can actually do this here. Now we're talking about three variables, right? Three components of gamma. So there are no constraints. What about the singularities? Do we have singularities or not? So this is the thing. Do we have singularities or not? Let's see. Here we do have singularities. Why? Because I construct R in terms of Euler angles. So I need Euler angles at each time. Each time I need Euler angles to get my R. Because this R is very important. I need R to march my dynamics forward. My dynamics may have loads in the inertial axes, and I write my equations in the body axis, so I need to transform, or vice versa. I always need access to the rotation matrix. You decided from the beginning to write the rotation matrix in terms of these three angles, so please provide these three angles at each time. Okay, here are the dilution equations. You can get that, but this particular equation has a singularity, like we said, we have seen last time. This situation is not here actually, luckily. Why? Because you construct R in terms of gammas. So just give me gammas please at each time. I can construct my R easily and I'm done. Okay, here are the gammas. Simply integrate your omegas. That's fine. There are no singularities from this point of view. Okay? From this point of view. But, so, to construct R, so no singularities with respect to R construction. But actually there are singularities if you want to read back phi and E, particularly E. So let's talk about this singularity. It's when you have the other way around. When you have R, you want to get from R phi and E. This is the problem. Because I have this equation. I have R equals E to the negative gamma tilde, right? How do you get gamma tilde from R? So we're now done with this, okay? We're talking about a slightly different problem, which is, okay, if I'm given R, how can I get my gamma or phi and E? This is the thing, okay? What is gamma or phi and E? What's that? Okay, you have R, here is the relation. Please get gamma tilde. So gamma tilde is ln R and you have the negative, okay? And you know that the logarithm has a singularity. This is the problem. This is the issue. So this has a singularity when R becomes identical. So if you start with an aptitude and start to do some maneuver and come back to this identity matrix again, this will give you a singularity. You will not be able to read the gamma tilde. In particular, actually, we have something called Rodriguez parameters or formula. Gives you cosine phi in terms of the rotation matrix immediately. This is the trace of R minus 1. You know the trace? Just sum the elements over the diagonal. This is the trace. Just subtract 1 and divide it by half. You get immediately cosine the rotation angle, phi. What about the direction? This is the magnitude of the rotation. What about the direction E? Here is a formula for it. This is the Rodriguez formula. 1/2 sine phi. And you can see now R23 minus R32 in terms of R. We're saying that we're given R. So this is in terms of R entries. R, this is 2, so 3, 1 minus 1, 3. And this guy is 1, 2 minus 2, 1. You can immediately see here that we have sine phi, so if phi equals 0, i.e. the rotation matrix is identity, we will have a singularity. We're dividing by 0 here. So this is the problem. In other words, you can always get E by considering the eigenvector associated with the unity eigenvalue. But if R equals I, it has 3 eigenvalues is 1. So which one are you going to take? So this is the singularity here. But in terms of integrating your equations, no problem. Any questions so far? About any of this? We're done with rigid body kinematics.
What will happen if identity matrix, we have got 3 eigenvalues? So if we take the eigenvector associated to any one out of them, what's going to happen?
It's not definite, but not well defined, right? It's not well defined. Which one are you going to take? So as if you have multiple solutions, which one are you going to take? There was a question on
How is it possible that phi is 0? Because it's basic rotation we are taking, and that is how the whole.
Yeah, I mean, I'm doing a maneuver and I'm coming back. So phi is maybe, I mean, imagine this simple situation. I'm doing a roll maneuver, so my phi is increasing, and then the airplane or the submarine comes back to a phi equals 0 and maybe negative again. So in the point that phi equals 0 in the excursion, there would be a mathematical problem. Any question? Yes,
So
Bakshi.
the mathematical problem of L and R is when R becomes negative, right?
Well, R is a matrix, so there is no meaning to say R
So
positive
when
negative.
R is identity matrix, why there's no mathematical problem for R?
Because R is identity means that phi actually it corresponds to phi equals 0, phi equals 0 sine 0 equals 0 dividing by 0.
No, I mean for gamma 2.
Yeah, because this is logarithm not of a scalar. Yeah, I see your point. Yeah, logarithm of a scalar has a problem when the scalar equals 0. But logarithm of a matrix has a problem when the matrix equals identity. Okay. Okay, it's like the these guys are matrices. When we're seeing exponential of this guy, this is not trivial. I mean, it's not exponential of a number, right? It's exponential of a matrix, and it needs a complicated command in MATLAB to do it. And the same for the logarithm. I don't know if there is a command in MATLAB for logarithm of a matrix or not. But we have formula anyway, Rodriguez formula, thanks to it. So, moving forward, any question about rigid body kinematics in general? We're done with rigid body kinematics. So this summary gives you the whole story of the rigid body kinematics. Do you have any question about specific detail in this table or the overall picture? Any question? Rigid body kinematics is an essential topic. Yes?
For the inverse principal axis, are you just solving for the body being rotated, and you don't care about the initial frame anymore, right? Is that what it's trying to do?
The role of the rigid body kinematics is to keep track of the rotation matrix, given the angular velocity vector. This is the kinematics. The dynamics gives you the acceleration. You simply integrate it to get the angular velocity omega. Given the angular velocity, please give me a way how to keep track of the rotation matrix. Here is a way, just integrate the components to get gamma and use this gamma to construct your I. Or here is another way, use these omegas into this equation to get 3 angles and use the 3 angles to construct your R. Here is another way, use your omega to solve this 9 differential equations to get R directly. Okay? Any question? Okay, let's talk about principal axes of rigid body. So when you have a rigid body, you know the ability to oppose motion. Yeah. What is the ability to oppose translational motion. Why it is harder to move particle or body in a translational motion? Why it's harder for a body than another body?
Mass.
Exactly, mass. For a translational motion is the mass, right? Because F equals mass times acceleration. If you want to exert the same acceleration for a larger mass, you need larger force, obviously, right? This is for translational motion. What about rotational motion? For rotational motion, it's not the mass in particular. It's the moment of inertia, right? So to rotate a rigid body about some axis, it opposes you by its mass moment of inertia about that axis. Okay? So we have mass moment of inertia about x, y, z, and maybe mass moment of inertia about some inclined axis, right? So we are interested in the following. We have mass moment of inertia, r, about some initial axis. And if you rotate, the mass moment of inertia will change, right? How will it change? We want to know this. How the mass moment of inertia will change under transformation of form, under rotation of the rigid body, okay? So I have I in E frame, for example, and I'm going to I in the B frame. The E frame and B frame, they are related together by what?
Rotation.
Rotation matrix, right? Is it simply multiply? We always do it with vectors. Multiply the vector in the old frame by the rotation matrix to get the vector in the new frame, right? This is the rule. What about the rotation? What about the inertia matrix? Should I just multiply by the rotation matrix as well? This is the question. Let's see. So we have some basic principles here. You know, what's the basic principle for the how I shows up in our dynamics course? Well, of course, it shows up in the angular momentum. So this guy is simply I times omega. And this can be written in any frame. In particular, maybe it can be written in the E frame. And it can also be written in the B frame, the body frame, for example, or the new frame. Any question about that? Can you tell me a relation between the angular momentum vector in the body frame to the angular momentum vector in the E frame? What is the relation between them, please? What is the relation? How can you go from here to there? I have this vector. How can I go from here to there?
Omega.
I have the angular momentum vector in the E frame, and I want the angular momentum vector in the B frame. How can I do that? How can I do that?
Through omegas.
What omegas?
Angular velocity.
Right? I mean, we just said it several times. If you have a vector in the old frame, I want to go to the new frame, simply multiply by the rotation matrix. Right? So this is in particular R from the E to B frame. Now we can substitute. This guy is IB in the times omega B equals R. So R to me is always from old to new, from E to B. HE I'm going to substitute from here, which is IE times omega E. Okay? Again, can you please tell me how can I get the angular velocity omega B from omega E? How can I do that? This guy is equal to, what is the relation between omega E and omega B? R. So I always multiply the old by R to get the new. Okay? Any question about that? Any question? Well, now I can simply write this equation, which is IB R equals R times RE. correct? Because both are multiplying omega e. So I got the coefficient of omega e. Yeah, so this is the equation, how I, the inertia matrix, transforms. It's not simply multiplying by R. Actually, if you want to get the new I need to multiply the whole equation by R inverse. So this is the final relation. I nu is equal to R times I old times R inverse, and luckily R inverse is simply the transpose. So this is how I transforms. This is how I transforms. It's not simply multiplying by the rotation matrix, you have to multiply by R from here and R transpose from there. Okay? Any question? Yes, please.
In both, the R is same in both the cases?
Yes. What do you mean symbol? Yeah. We
Because
have
once
we have two frames, one called E and one called B. It's a single R that transforms every single vector here to every single corresponding vector there, right? It's the rotation matrix that relates the two frames. And this
same-
R is relating E to B, from E to B. Yes, single R.
Same R transforms from B to E to, like,
No, it's the transpose of it. But I didn't do that. Where I transformed it from B to E. Here, I got some in the E frame, some vector in the E frame, to relate it to the B frame, right? But always, not to confuse yourself, always multiply the old vector by the rotation matrix to get the new. The same here, I'm replacing the new. What is the new equal to? It's the old vector multiplying the rotation matrix. Okay? Any question?
So just to have this like solidified in my head, whenever you multiply a vector by the rotation matrix, that's, you just get the transformed vector.
Exactly.
But not when you do a matrix like the
Yeah.
rotation matrix.
Yeah, so this is the thing. If you want to transform a matrix, here is the way to do it. Turns out not to be that trivial, like a vector. And this actually raises a question. It raises a question. What's the question? Well, if I really changes by rotation, I have I in an old frame, now I'm in a new frame, and these two I's are different. So in particular, I's can increase, decrease. So the question is, how the body can rotate to attain its maximum, axis of maximum inertia. So you have some inertia here, and if the body rotates, as the body rotates, the inertia changes, right? What is the rotation that delivers the body from any given inertia to the inertia, the maximum inertia, axis of maximum inertia, which we call